So the project contribution document is it is finalized. It's to the point where I'm not making more changes to it. So take a look at the new details. As some extra information about how to test your new features. I changed the code to office hours just a little bit. So make sure you have, if you already forked, make sure you fork the new version or pull the new version, merge those changes into your new code. The change I made was adding an easier way to test your code. So instead of requiring a MySQL database running, I gave this testing database, which just uses a list, just data structure stored in RAM, so it does not persist. We lose the whole point of using a database in that the data doesn't persist, but it will let you test your features, run the app, make sure your features work with this thing, so you can actually run the app locally and test it without either installing MySQL and get that running, a MySQL server, or Docker with Docker Compose and running that. If you do want to use the latter two, or if you're making changes to the database itself, you should definitely test those changes. I'm in the wrong document. You should definitely test those changes. So I gave some procedures on how to run either MySQL or Docker here, and MySQL here, MySQL without Docker, or MySQL inside Docker, and running the entire production environment. This production environment, this is how I'm running it on the server. So if you want to simulate that server completely, or if you want to deploy this on your own server and test it out there, this will run the apps on either ports 9005 or 9006. You can play around with that. Something special to show you at Q&A. Took me about an hour to make. Okay, I'm looking forward to it. Were there any changes in the server database in student and queue files at all? You have to check it out. I don't remember exactly. Well, I might as well. Hey, it's worth showing you how to do something like this. So if you go to student and queue, well, right away we can see last change 4 days ago. So no, and my last commit for that was initial server setup. So the student and queue class itself was unchanged. And if you look at any file, you can click the history and look at all the commits that changed that file. So it looks like no. Do we just choose one of them to do our office hour? Yep, it's up to you. Either one. It's just like the homework. I wanted it set up in the same way with the homeworks, is that you have 2 different assignments that you can work on. This is part of the reason why there's only one homework for the 5th application objective. It's because I wanted to make sure I had the energy to make 2 separate assignments for the project contribution, which takes quite a while to set up to get everything just right for these. So you have the 2 apps, the to-do scheduler, the initial code is there, the app is live. I'll hold my breath a second to make sure it works. I should be able to add a task, and I can mark tasks as complete. So very basic, very bare bones. The intent here is to not give you very much functionality, giving you almost no functionality here. So there's a lot of room for improvement. You can use this for a few seconds and think of probably 5 to 10 features that you'd like to add to this thing. And that's the way I want it. I want no shortage of ideas to figure out what you want to implement. And if anybody's playing with this, I should be able to see your updates live. I'll stay on this for just a second just to make sure everything's working. But I should see your tasks if you add one. Somebody wants to add one. Preferably non-offensive. Why does the server say could not find or load main class model.office hours server when I run it? I don't know. We'll have to talk about that. Did you go through the whole document and read all this stuff? If not, well, regardless, we can talk about that during Q&A. Yeah. Say hi to Jesse. Give Nicholas a 1-0. I'm sure I gave you a 1-0 on at least one objective, so I completed that. And somebody else, I'm not going to say hi to myself, so read this. I read it. Please give me an A. Well, anyone with this U bit, I'll give an A to. All right, so let's get into some slides and talk about some juicy content. When do you expect homework 4 grades to be out? Over this weekend, I'll be doing a bunch of grading. Homework 4 is the next thing I'm grading for this class. I also have a project phase to grade in 312, so that's going to take up a lot of my weekend. I might not get much more than just homework 4 graded. I was hoping to find some time earlier this week to do homework 4, but I just had so much other stuff. Take your time. I do feel the constant pressure. I am behind on grading. I do feel the constant pressure for that, and I'm constantly trying to find time to do grading. So don't think I'm just sleeping on that. I just always have other things. Mostly lectures, getting 6 lectures ready per week. That's usually what's taking up my time. And then all the little emergencies that come up constantly, I got to prioritize those. And then I just unfortunately didn't find time to grade this week. And last weekend I was doing other grading. I was getting homework 3 out. Man, was I that late with homework 3? Anyway, I'm getting to them all. This weekend is just a lot of grading for me. I want to try to get caught up on some things. I got Learning Objective 4. We have the Learning Objective 5 lab before Learning Objective 4 is graded. I don't like that. I don't like doing that. I'm trying to get caught up, and I do feel that pressure, just so you know. So last time we saw a GUI where we inputted a degrees in Fahrenheit, clicked a button, and then converted that degrees to Celsius and displayed that Celsius degrees. We did that by adding 2 display fields, one of them that's non-editable. I shouldn't even try to pronounce that word. And then a button. And then added all those to our layout, added those to our scene, and got all the elements to display. The big piece of functionality here, the event-based architecture side of this, was adding a button listener to the button, which has references to both displays, and then that button listener, when it's pressed, it will receive the handle event. It'll get the action event called through its handle method. It'll get the action event, which is clicking on the button, and this event is going to have all the details of that event. For our purposes right here, we're not concerned with that event at all, any of the details. Was it a right click? Was it a left click? We're not concerned with that for our purposes here. But we do want to know, okay, this button was clicked. Let's pull the degrees Fahrenheit, convert them to Celsius, and then go to our Celsius, our output text field that has the Celsius, and set its value to that degree Celsius. So we got some good functionality there, and that's cool and all, but what if we want graphics? So you're pretty limited if your app only contains these GUI elements, buttons, text fields, text areas, radio buttons, checkboxes, things like that. We can do all that. I'm not going to go through each type of element, but as I mentioned last time, there are tons of tutorials. You can take a look at what's out there. If you want to do drop-down boxes and things like that, you can get, if you want menus, you can build full GUIs with everything but graphics with what we just saw. There's no new concepts there. It's just more application of the same idea. So it's stuff you can go find the documentation on, find a J combo box or a combo box. That's what they call a drop-down menu, and then get your stuff, get all your GUI going on with that. But let's talk about graphics. This kind of is a new concept. So let's talk about how to add graphics to a GUI. So we'll focus on 2D graphics. You can do 3D graphics with ScalaFX. There are classes for that. There's support for that. I won't go over it in class, but again, feel free to check out the documentation. There is 3D support. You could build a full 3D game with this library, or 3D simulation, maybe a traffic simulator with 3D graphics so you can move around the world. All that's possible with this library. Once you have the foundation, you can build on that and be able to do that. The jump to 3D is quite a bit. You have to worry about cameras and camera angles and stuff. But let's talk about 2D graphics. We're going to keep this very simple for this class. And since I'm not even asking you to make a GUI this semester, feel free to do it anyway, but to understand the GUIs here. But we are going to keep the examples very simple. They're just going to be squares and circles. Just simple shapes. Add them to a GUI, and we want them to be able to move around and also interact with user inputs. That's what we want to get to in today's lecture. And I let this note in here, even though I'm not grading your GUIs this semester. But even if I was, this is not an art class. I would never grade you on how visually appealing your GUIs are. I want to focus on the technical aspects. Were you able to get the functionality that we want? This is something I do in all my classes. My 312 students know this too. Their front ends of their websites, I really don't care what they look like. as long as they have the functionality. If they can build file uploads with streaming content and DMs and things like that, that's what I'm concerned about. I really don't care about the styling. That's just maybe more something with me, but with computer science classes, I want to focus on the science, not computer art. So I left this in there just to let you know where I stand, I guess. But let's talk about adding graphics to a GUI. So the first thing, one of the most important things to know when working with computer graphics is the origin. And this is pretty standard with images, screens, everything. The origin is the upper left corner of the screen or image or video. The upper left corner is 0, 0. And then X and Y go in the directions you would expect. Positive Y is down, though. You might expect the origin to be down here. Positive Y being up, like a typical grid system that you see in math class. Screens do not work that way. It starts at the upper left. Y goes down. X goes across. So that's the number one thing that takes some adjustment, is understanding where the origin is. And when you get XY coordinates, where is that on the screen? Looks like Python. It's a blue rectangle. So let's see how to add elements to this to our screen using 2D graphics. So the syntax, not too crazy here. You have to specify if you want a 2D shape. Again, I said squares earlier, but rectangles and circles we'll stick with. If you want some shape on the GUI, that shape, for basic shapes, is going to have a class with that name. Create a circle using the circle class. This is not a class that I wrote. This is part of the ScalaFX, JavaFX libraries. So I'm going to create a new circle. A circle needs to know where it is. With a circle, we specify the center of the circle. So this would be, if this were the origin, the upper left corner of the screen, this circle is going to go 20 over and 50 down, and that's the center of this circle. Then we specify the radius. I'm going to say this radius is 20, I believe, pixels. Are those measurements? Of course, they're doubles, so 20 units for the radius. And then I'm going to specify the color. There are a lot of predefined colors, or you can work in RGB values. Just provide the RGB values to get the color. I'm going to use the predefined colors and just make this a plain old green circle. Is it to take percent or VW or VH values? I don't know what you mean by that. Vertical, I think you're thinking like CSS stuff. We don't have that CSS functionality, but we could read the size of the screen and then compute those ourselves. But there's no built-in, not that I'm aware of, no built-in functionality for that. And then rectangle, same idea. We have the translate X and Y to get its location. This is going to go 60 over and 10 down from the upper left corner. And that's going to define the location of the upper left corner of this rectangle. So it's important to know if you want to place a rectangle and put it in the exact right location. Translate X and translate Y are specifying from the upper, I might as well go to my upper left. The upper left corner of the screen, this is going 60 across in the X direction and 10 down in the Y direction. That's the upper left corner of the rectangle. And then from there, we're going to specify the width and height to figure out where to draw this rectangle. So, once we go 60 over and 10 down, this is going to go another 60 over and 40 down. And those 2 points are going to define the rectangle. So this would be 60 over, 10 down is the upper left. Another 60 over and 40 down is the bottom right. And then all of that space defined by those 2 points, that's what's going to define the rectangle, and that's what's going to be colored in with whatever color you specify. Once we have these shapes, I was on the wrong slide. But that's all the stuff I said on the previous slide. Now that we have our shapes, we define these. Let's see how it fits into our program. I'm going to create a new group of elements. So there's no sense of a layout when we have these 2D graphics. the 2D graphics, we're specifying their absolute positions and sizes. So it wouldn't make sense to put these in, say, a VBox, because we are telling the GUI exactly where to draw these shapes. So we're going to put those in a group, just unordered list, an unordered container of GUI elements. We can put these in a group instead of a VBox, HBox, grid layout, whatever. Those don't make sense here. So throw them in a group, and we're going to throw that group in the content of our scene. And we're also going to do one more thing. I'm going to specify the width and height of the window. So before, with our calculator, I put some GUI elements on the GUI, some things for the user to interact with, and then I just created the GUI and threw those elements on there. So if we go back and look at that, the size of this window was as small as it could possibly be while fitting all of my elements on it. So the GUI sized itself to make sure all of these components can fit on the GUI. When I'm doing that with my shapes, I'm not sure what size I'm going to get for my GUI. If I just say, here's my shapes, resize how you will, it might resize to just fit these two shapes on it. But if these shapes are going to be moving around, I might not need that size. I might need a larger size. So I'm going to specify my size, or I never even tried it because it wouldn't make sense to even do. But it might not even show these elements. I don't even know if it has a way to know that these have been drawn on when it resizes. But anyway, when we're working with 2D graphics, we're going to specify the width and height. And that way we can know exactly how large this window is. We can know, if we're building a game, we know the exact size of the playing area, or at least the visible area to the user, if we have that height and width. And we're going to know that height and width by telling the GUI what the height and width is going to be. So we specify the height and width, and then put our graphics on there, and now we have a window with the size, a known size, and then GUI elements, 2D shapes on that window in locations that we know, known locations. So we know what this GUI is going to look at, no matter what the screen size is going to be. If the screen size is, as long as the screen size is larger than the GUI itself, we're going to get things rendering, I should say, get things rendering the way we want it to. And here's what the full app looks like. So I specify the window height and width. I went with 800 by 600 here. Storing some variables to store some of this information. I'm creating I did expand this a bit. Let me explain this a little bit then. So when I get what should I do? Yeah. So when I create this GUI, I'm going to have the player represented as a circle. Just like in towers, the player is a simple circle. I'm going to specify that player as a circle with some random starting location and a radius specified by whatever I said it's going to be here, and make the player green. I'm going to add that to this group that I'm creating, same like I did before. I have a group containing all of the GUI elements, and then I'm going to add that player, that group, to the scene that contains only the player. But whenever it's on the next, it's going to be on the next slide, but all the rectangles, which I haven't mentioned yet, are going to rotate with time. So I guess I'll talk about this part before we even introduce a rectangle, but trust me, there will be rectangles. I thought I showed all the code on this slide, but some of it's to come. So this update method, or rather this action timer that takes an update. You know what? Let me just let my slides guide me through it. So I'm specifying the height and width, and this update, this action timer that takes a function of type long to unit. It's going to take a long and return nothing. This update function is going to be called, presumably, or it's going to be attempted to be called at 60 frames per second. So 60 times per second, this whatever function is given to the action timer is going to be called by the GUI. And this is how we can get some movement, get some fluid animations and stuff in our GUI, is by using this action timer, telling it to start. That's going to call whatever function we give it 60 times per second. And the long that it's given is going to be a timestamp, just like in Clicker, where we have that timestamp that we're working with, that system.nano time. We're going to get a timestamp, and then we can do whatever we need to do with that. I am just going to iterate through all of my rectangles, ignore the time completely. So I'm just going to rely on the frame rate being okay, which won't always be true. This isn't something I'd want to use in production and something I'm going to deploy. But I'm going to iterate through my shapes 60 times per second and just rotate them by half a degree. So I should get 30 degrees of rotation per second with this function. So this is a way that we can add a sense of time to our apps, which we use actors for this. I actually used to teach this course in a different order. We would use GUIs and leverage this to get our real-time interactions, and then introduce actors later. And then with actors, the advantage is that we're not confined to 60 FPS. So if we want to update physics, maybe we don't want to do that 60 times per second. With graphics, 60 FPS is fine, but we might not want to update every aspect of the game 60 times per second, for what it's worth. Side note. Oh yeah, and I should have updated the slide. But when I made this slide, we didn't know about first order functions yet. You all know about first order functions, so we're good on that. Oh, hey, actually, this one got by me. This slide, this whole thing should be gone. This is what first order functions are. Y'all are pros at this. I ain't gotta worry about you. I got way ahead of those slides. Sorry about that. So update is rotating rectangles, but those rectangles don't exist. I never created a rectangle, so this is really kind of pointless right now. So let me add some code to this to get the actual to actually get rectangles on this GUI. So with so let's get some rectangles on this GUI. I believe this was one of the early labs. This is one of the pieces of software I asked you to run to make sure that you had all the libraries installed properly. I think you actually saw this way early in the semester. So let's see how it all works. Back when we were on campus, this was one of the early labs. It might have been the first lab, actually. So we have this draw rectangle method, which is going to take the center of a rectangle. Say, I want a rectangle centered at the inputs as X and Y. So we'll create a rectangle. We'll have some predefined height and width that every rectangle will have. And then the translate X and Y, remember that the translate X and Y is for the upper left corner of the rectangle. So we're going to do a little bit of math. If the center X is this where we want it, we're going to have to translate that by half of the width to get it the upper left corner to where it needs to be. So the upper left corner is going to be the center minus half the width. The upper left corner Y is going to be the center Y minus half the height. So we're going to get that translate X and Y to be the upper left corner, not the center, as it should be. So we want to give it the center. That's the functionality we need. That's the functionality we want for this case. And we're going to translate that inside this method to get translate X and translate Y to be the upper left corner. And we'll make them blue. Add that to our graphics container. And then add that to our rectangle so we have a reference to just the rectangles. Scene graphics also has the player circle. We don't want to rotate the circle. We're going to store the rectangles separately, and then we can rotate the rectangles through this data structure. And Okay, so when is that going to be called? This is the last part I wanted to talk about. When is this going to be called? When are we going to have the center of a rectangle and add a rectangle at that center? Well, I want to do that whenever the user clicks on the GUI. So I want to respond to a mouse click. I want to get the X and Y values of that click, and then I want to add a rectangle at that location. That's the functionality we want here. That's what we're going to build here. So inside the scene itself, we're going to add an event handler. So we're going to react to a certain type of event. That type of event is going to be a mouse click. So similar to when we're passing messages for the past 2 weeks, except we're reacting to a specific type of event which is not a message. We're going to react to a mouse clicked, an event of type mouse clicked, and we're going to create our new mouse event handler, which we have up here, which is any class that extends event handler of mouse event. So we want to handle mouse events, events of type mouse event. We're going to have a handle method, which takes in the mouse event. So this is the same as the button, which had an action event listener, and the action was that button being clicked, and that's when that handle method was called, when the button was pressed. We're doing similar things, similar setup. We're still using event handler with a handle method, except the type parameter is going to be a mouse event instead of an action event. And then whenever this mouse, the mouse is clicked, in this case, we can listen to different types of mouse events. Mouse scroll, mouse drag. There's all kinds of different other mouse events, the things you can do with the mouse. But we're going to listen for the clicks. And whenever that click happens, this time we are, as opposed to that button press, this time we are going to extract some information out of the event. And being a mouse event, this object is going to have a getX and getY method, which will get the X and Y coordinates of the mouse, again, measured from the upper left corner of the screen. You're going to get that exact location of that mouse click. So you can react to the user's mouse clicks by getting that XY position and then adding a circle or adding a rectangle at that location, add it to our data structure so it renders, displays to the user in the next 60th of a second at most, and adds it to the all rectangles data structure so the thing starts spinning. I talked about that slide. Talked about all that. And I want to, before we get too far into this, I want to go to the GUI and run this thing just to make sure it's clear what we're talking about before we get too far into this. Must be this one. Before we get too far away from reality and forget what we're actually doing, I want to show off the GUI so we're reminded what's going on. So here's my GUI. Here's the player. We'll talk about that in a second. And whenever I click, I should get a rectangle. A spinning rectangle that spins 30 degrees per second. And I can click, place all kinds of rectangles. If I stay in one spot, I can make a neat shape. Oh, I moved the mouse a little bit. And get that functionality that was promised in the slides. Another piece of functionality we have here, which is the next thing we'll walk through in the slides, is that when I hit the arrow buttons, when I hit the WASD buttons, the player is going to move around. Apparently I didn't hook it up to the arrow buttons, but we can talk about how that would happen too. I can move this player around, so I have a little more interaction with the user. So with this is the foundation of having a user that can interact. I can make mouse clicks, run some code based on a mouse click, and I can press the button keys. And of course, this is concurrent. I can do these things concurrently. So if you have something where some piece of software, probably a game, where you have the whole keyboard, you have every key that you can react to, and also mouse clicks that you can react to, you can get a lot of functionality here. Then after that, it's a matter of coding things, getting better graphics. Instead of square rectangles and circles, you can render JPEGs or GIFs or whatever on here. You can just specify an image file and have that render. Have one background file for the background. You got everything you need to build a cool desktop game here, or build your front end in web technologies. Build your WebSocket server. Hell, even throw in a bottle server. With what you know now, you can do quite a bit of cool stuff. Is there a cheat code? Yeah, well, fortunately, there's no win condition here, so. But there is a cheat code. There are libraries to take over the mouse. I could simulate mouse clicks. We could write software to do that. Hey, if you're interested, we could do that during Q&A. All right, so we got all the rectangle functionality. Everything you see with rectangles there, we got that down. Now let's talk about the player movement, and that'll kind of wrap up our talk of GUIs. So with player movement, I want to react to WASD. Yeah, I didn't do the arrows here. You could do the arrows too. I believe the key codes are like arrow left, arrow right. I don't remember actually off the top of my head. But there are codes for those strings that match that key. So in my GUI, I'm going to listen for another type of event, a key event, and I'm going to trigger it every time a key is pressed. I'm going to send the event that was triggered by that key and send that to my key event handler. And I want this class, which of course extends event handler of key event, and I'm going to give it my player so I can learn some information about the player and also modify the player in reaction to this event. So we have a few different key event types. I could do pressed, released, and typed. I'm doing pressed, so I want this to trigger whenever somebody pushes the key down. Whereas key typed is a down and an up, like you actually just type that key, and released when somebody lets that key up. So you can react to these three different events, so you can get some fairly complex functionality. You can use these events to tell if a key is being held down and things like that. I'm just going to read pressed, which if you hold a key down, the key pressed event is triggered at regular intervals. So when we were on the GUI, I was just holding down one of the buttons, and that key pressed event is constantly firing off. And you can see it kind of jittery, the movement on that, because I'm not doing any physics at all. I'm just reading those key press that are sent at regular intervals and then just moving the player based on that. So when I do get that key pressed event, try to not get ahead of my slides again. So when I get that key pressed event, I'm going to get that key event in the handle method. That structure should be looking very familiar to you by now. And I'm going to call another method. I'm just going to defer to keep this fairly clean. And give it the code of that event. The code is going to be the key code specifying which key was pressed. So each key on your keyboard, and some that aren't on your keyboard, have a specific code. And I'm going to check that code using a match case statement, which is similar to a switch case in other languages, except it does some type matching as well. We've seen these in actors when the receive method, we're using cases to check the type of something. In the equals method, when we overrode the equals method, we use the match case to check is what I'm comparing to the same type of what I am. If it is, then do some comparison. If it isn't, just say false. We're not a match. We're not equals. Here we're using it to check the name of the key code. What key was pressed? And we're not doing any type checking here. We're only going to check strings. But we're going to say if that name was W, run this code, because the player is, I had to look at the keyboard for that. The player, feel bad about that. W is going to be up, so I want to subtract from the player's translate Y value. And whenever that value changes, the GUI on the next update cycle, so at most the 60th of a second later, it's going to notice that translate Y has changed and actually move where that player is displayed on the screen as soon as that value changes within a 60th of a second later. I'm going to subtract from that the player speed. I just pick some arbitrary number here and say every time we get that key down event, we're going to move the player this many, I believe pixels is the unit of measurement here, this many pixels, 10 pixels up. And notably, we're subtracting from y because, again, the origin is up here. So if I'm here and I want to move up, my y value has to decrease to be able to move up and increase to move down. So the y-axis, remember, it's inverted from what you're used to in math class, statistics class, and everything else. Anywhere where you drew a graph, any science classes, we have an inverted y-axis. And then the other keys, ASD, adjust, translate y or x appropriately, and then that player is going to move. And if I hit a button that isn't one of the ones that I expect, when you saw me I hit the right arrow button, it's going to just display that key was pressed with no action. Actually, right. So the event is right for the right arrow, so it must be right, left, up, down, with capital first letter and lowercase rest. So if you want to react to the arrow keys as well, that functionality is there for you. Everything's there for you to play around with. Oh, we're at the end there. Done with this one. All right, so let's talk about a model of architecture. You've seen this throughout the class. We're not going to get to MySQL today. We'll have to punt MySQL off until Monday. But let's talk about some architecture. So much information today. That is a lot. It's fast. But I can also go, like, I take my foot off the brakes for these ones. I mean, I always go pretty fast. But since you're not required to do a GUI for your grade, this is kind of bonus content in a way. I should probably change that in future semesters. I always used to require GUIs, but for some reason I didn't this semester with the learning objective setup. But I can go faster since it's all bonus content. Plus it's all recorded, just rewatch it. How come for the physics engine GUI, our z-axis was the one that was positioned up and down rather than the y-axis, like it is like in the most recent GUI? So it's the difference between a 3D GUI and a 2D GUI. For physics engine to work, so you can use physics engine for a 2D GUI, and to keep these consistent, I always think of the physics engine. If you're using that for 2D, you have a top-down view and you're looking down on the grid. Just like the app that we just saw, that circle was moving around and we had a top-down view. If you have a top-down view, you're looking in the direction of the z-axis, and you can see the x and y, and x and y is where the game is. And then for jumper, where I do have vertical, that is the x and z-axis that we're looking at. So that gets a little trickier to think about when you have an x and z-axis and x and y for your screen, but x and z for your game. Does get a little much, but we can write classes to convert between those, so we can think of just one coordinate system when we design our games. And blah blah. Let's get some more content in your head. Let's get some more information out there. MVC. This you've been seeing all semester, but I want to focus on the learning objectives for those first 11 weeks. Unfortunately, I just couldn't fit this in anywhere. I wanted to do it during the OOP section, but there's just no time. I have to talk about so much content in those 2 weeks, so it gets punted down here. But you've seen this a lot. Let's talk about what this is and why we do this. So the MVC is an architecture pattern as opposed to a design pattern. You saw the state pattern, which was a design pattern. How do I have this problem in my code? How do I solve this one problem and get this piece of functionality? As opposed to an architecture pattern, MVC is saying, okay, I'm about to write some software. How do I organize the entire project? How do I organize my code into packages, into modules? How do I think about it at that level before actually solving any problems? MVC doesn't solve any coding problems for us. It solves organizational problems for us. So the key aspect of the MVC is to split our code. MVC architecture pattern is to split our code into 3 pieces: model, view, and controller, and then completely decouple these 3 pieces and have as have them communicate with each other to be able to get the functionality we need to get a full app up and running. So these 3 apps should be tested independently, developed independently. They can be worked on by separate parts of the team or separate sub-teams. If you're in a team, you might have the controller team, the view team, the model team, if that's how you have it set up. And that should be easy to do because these are very decoupled from each other. With this, we'll be talking about the acronym API quite a bit. I've been using this throughout the entire semester, so it should feel pretty familiar by now, but I want to take at least one slide to really just shine a light on this acronym and say kind of how we use it. So in 1.15, you've seen web APIs, you've connected to web APIs, and those APIs had endpoints that you accessed through a path. You made an HTTP request to that path, and then the API gave you some information back. So that's that's one example of an API. But an API can be any set of functions or functionality or methods that can be called. It's really however you interact with a piece of code or a piece of software. And I should say, I don't even have on the slide what the acronym stands for. It's an application programming interface. So it's the way that your program interfaces with an application, or how 2 pieces of code interface with each other. So it can be any set of functions, functionality, or method calls that can be made, or HTTP calls in HTTP requests in the case of web APIs. Any way that you access a piece of functionality. So inside that code, there can be all kinds of stuff going on that we don't need to know about. But if you need to use a piece of software or use some functionality from somebody else, you go to its API and it'll say, I offer these methods that you can call, and then we can call those methods and not worry about the details of how those methods are implemented. This is how all of your stuff is graded in Autolab. In the lecture question, in the homeworks, in 115, in the project, and everywhere, we say, this is the API you need to implement. Write a method named this that does this, takes these inputs and these outputs. And then how you implement that is up to you. We don't have to know, the grading scripts don't have to know how you implemented that, as long as you implement that API and get that functionality that's needed. So all of you can write your code in very different ways. As long as you adhere to that one API, we're going to be able to use that code consistently. So the API is a way to separate the how does this work, and the what does this do. Like, you never understood how those web APIs actually served up that content. Like, you can get an idea of how the server itself works, but you don't know how it stored and processed its data. You don't know that code. You can't see that code. And you also don't care. That's the big advantage of APIs. You don't care how they got that code, that information to you. As long as they return to you a JSON string in the right format, you're happy. And that's why we use APIs. And that's the idea with that. When we were talking about the state pattern, we talked about APIs extensively. Define your API, and then the states implement that API differently. Each state will have a different implementation of that API and different functionality for that API. But anything in the outside world just calls your API to get that functionality. There's a lot of detail that goes into how Autolab works. We could definitely talk about that in Q&A. I'd be happy to talk about it. So we can change functionality as long as our API stays the same. We cannot, or rather we should not ever change, I shouldn't say ever, but we shouldn't change an API without really weighing the consequences of that. For the project contributions, APIs are going to change constantly. That's just going to be a part of that. We're going to have all kinds of incompatible code. It's just, what's going to happen. But when you have code that's out there and deployed, you cannot change your API. We talk about this with the ISS, HTTP API, the web API for ISS. Their lat and long that they return are strings. And I always mention, why are these strings? I feel like they should be doubles. But at this point, they can't make that change because any code that's written to interact with that API will break if they change those to doubles from strings. So we can't change an API without weighing all the consequences of that API, but we can change the functionality. So for example, if you have your physics engine, which the API is the update world method, give me a world, give me a DT, and I'll update all of the physics in this world. I'll update all the dynamic objects. If we want to add dynamic collisions, so if you want to go back to your physics engine and do the expansion objective to add those dynamic collisions, any code that uses that API is still going to be fine. When you add dynamic collisions, you don't have to change anything in the jumper code to get those dynamic collisions working. Jumper just interacts with the API, which is the update world method, and gives it the whole game world, and then the physics engine takes it from there. The physics engine cares about all these collisions and everything, collision detection, and the interactions, velocities, and all that. Jumper itself doesn't really care about any of that stuff. So it still accesses the same API, and if your physics engine is updated, you implement dynamic collisions, you now have dynamic collisions inside Jumper because you were coding through an API. Jumper calls this API, you didn't change the API. If you added a parameter to the update world method, you just broke everything. Anything that uses that physics engine is broken now. But we have this very simple API. Give me a game world, give me a delta time. Everything else is handled inside the engine. So we can implement the physics engine. When you first get the handout code, Jumper just doesn't have any functionality, but it's still calling update world. And as you add functionality to your engine, you can see those changes in Jumper because we're coding to the API. So let's talk about MVC. That's enough of a sidetrack into APIs. Just a reminder of what those things are, and hopefully more like I assume you're more ready to hear more information about APIs. Where if I did that earlier in the semester, if we did that in 115, you might not care because you might not have really felt the effects of that. Anyway, MVC is split into model, view, controller. The model is responsible for the app itself and all the data of the app. And I always call this the core of the app. This is where all the action happens. This is, if I were to pick one of these three pieces, I don't know, maybe I'm biased, but I would say the model is your app. The model is your core functionality. That's where all of the good stuff happens there. That's where you actually get an app built. The view is only responsible for visualizing the app itself. This is anything that's displayed on the screen. The view is typically going to get a bunch of raw data from the model, and it's going to figure out how to render that to the screen. And then the controller is going to interact between the view and the model. It's going to grab user inputs and translate them into calls of the API methods of the model. So we don't want our model to have to care that there was a mouse click or a key press. The model is just going to expose its functionality through an API, and then it's the controller's job to figure out, okay, the user did this, that means I should call this API method. And it's kind of that liaison. And visually, this is what it looks like. The user is going to observe the view, get the information of the app, make some inputs, send those inputs to the controller. Those inputs are going to be translated into API calls of the model's API. Those calls are going to change the state of the model itself, and then the updated state is sent to the view, or more often the view is requesting the state from the model. That state goes to the view, and then is seen again by the user. So you can see this whole loop. The user sees something, does something, changes the state of the app. They see that change, they make more inputs, and just go around this loop as long as the user is using this app. Yeah, you could add a parameter if it has a default value. That's right. But then, yeah, that'd be fine. So the model, core of the app, this is pretty much everything you've written so far. Most of all the homeworks I give you, when it's split into packages, model, view, controller, I give you the view and the controller, and then the model is your task. In this model, build the functionality. And then you can run my GUI run my view to see the changes. You run my controller, use my controller to translate mouse clicks and keyboard presses into, or button presses, into calls to your model through the API. But the model is where you're really doing your work. You're building that core of the app, the real functionality. For example, you built, some of you anyway, built a physics engine. If you didn't do rhyming dictionary, you built the physics engine to handle the physics of Jumper, and then Jumper took that game world and rendered it to the screen, and it took the user inputs and sent them to where they needed to go to update the velocities of game objects. But it was up to the physics engine to really do the mechanics, actually make that a real game. Jumper with no movement isn't a game at all. It's really boring. The physics engine is where it's really happening. That's where the good stuff is happening. If there's any data to be managed, this is where it's happening. Any data structures, database, everything related to this program data-wise, it's all happening in the model. And the model is removed. Thinking of this picture, the model is completely removed from the user itself. The model is not aware, or rather should not be aware, that the user even exists. That's how removed the model needs to be. It's the view's job to display things to the user. It's the controller's job to take inputs from the user. The model does not interact with the user, not directly anyway. The view is output only. No logic happens here. You should not be processing anything. Nothing should really be happening in the view. Just take the state of the model and show it to the user. That's the view's only job. That's all it does. The view can be any type of view. If we have a command line interface, you're in your command line and you go into an app and it just asks for text commands. It could be a GUI. It could be a web front end with HTML, JavaScript, CSS. It doesn't matter what the view is. And this is one of the beauties of the MVC architecture, is that the model can stay the same as the view changes. So you saw with our chat app, I had one model, one piece of the app talking to the database and processing events and reacting to events through its API. The API is, I accept messages of these types, send me messages of these types and in these formats, and I'll do the rest. I'll take it from there. And with that, it didn't matter if I was running the web front end or the desktop front end. Both front ends worked with the same exact model because they were both complying to that API of the model. So the views are interchangeable. They can be replaced, and we can even have multiple views without changing the model at all. And the controller is going to take those user inputs. We see this in the case in the form of event handlers we just saw, where we're taking user inputs and then processing those into API calls. So we don't want our model to ever have to care what an event handler is. We don't want our model to ever care what a WebSocket message is. We don't want our model to care what a case object or case class is, these message types. We don't want the model to care about any of that in the MVC architecture. The model should have its API, which is applicable to any format, any way that the user is interacting with it. It should not be specific to any type of interface. So the event handler's job is to take the event that happened, that occurred, and then translate that into a call to the model using one of its API methods. So if we need to change the entire look and feel of the app, we replace the view and controller, but the model does not change. So if we wanted to take Clicker and turn it into a mobile app, we build the view and the controller for that mobile app. Given the JSON game state, how do I render this in the app? And given some presses on the screen, how do I convert those into WebSocket messages being passed to the server? The server does not care that that's a web app. All of that code is reused. You have that one server. We have my Clicker server up and running right now. You could write a web app that interacts with that without rewriting any of the core clicker functionality. You just have to make a new view and a new controller. And the big part of that is the view. How do I, actually neither of those are too hard for clicker, is how do I render this stuff and how do I capture user inputs and send them over the WebSocket. I don't really want to talk about this stuff, right? And this is the slide I want to get to. I know I'm a little over. For the calculator, the model API is what you implemented for your homework. For calculator and microwave, they're both the same. The model API did correlate directly with button presses. That's not always the case, but in this case it was. But it doesn't matter what those button types were. If that were a desktop GUI, like it was for the assignment, if that's a web GUI with web sockets, if that's a physical calculator in the real world, it doesn't matter. We just need to translate those user inputs into calls to the appropriate API methods of the model. And then your calculator code that you wrote can work in any of those deployments. We can swap out the view and the controller at will. So that's the advantage of separating these model, view, controller. The model, you build that once, and then it doesn't matter where you deploy this app. You reuse that model code. That does not change because it's completely independent of anything user-facing. So you can change out the entire user interface and keep the entire model.